So far, we discussed the electrical circuits. Okay. So now we'll start the new topic. So that is known as transient analysis of electrical circuit. Transient analysis of electrical circuits. So far, what we learned, so that is the steady state analysis of electrical circuit. So that is the steady state analysis of electrical circuits. So that means, so there is no change in the values. Okay. So there is no change in the values. For example, if you obtain some voltage across a particular resistor, right? So that is, so for example, we have voltage across some particular resistor or particular uh, element. For example, you obtained as 22 sine omega t plus 30 degrees. So this is the voltage across a particular resistor. Sorry, not resistor, but maybe a particular resistor, for example, right? So in this particular case, so what you understood that, so this value is, so that is its steady state response. So that means this is a waveform, so which is varying something like this. Okay. So there is no change in the waveform. Okay. So whereas this the transient response, right? So here, so we can observe the how this waveform is changing, right, with respect to the time or with respect to the behavior of the elements. So that we will learn. So in this, right, so this is basically divided into DC transients and AC transients. So meaning is, in case of DC transients, the circuit is energized from a DC source. The circuit is energized from a DC source. In case of AC transients, the circuit is energized from a time varying or AC source. Is energized from a AC source. So basically, the circuit analysis so can be broadly divided into two types. One is the frequency domain analysis. Frequency domain analysis and time domain analysis. So in case of frequency domain analysis, so we will usually talk about the omega. So far whatever we discussed about, so in that case, the reference is omega t, right? So there is a frequency of the circuit or the frequency of the waveform. So now everything will talk in terms of time period t. So now everything will discuss or everything will talk about time period t. So with respect to 1 second, 2 second, 3 second, so how the performance, how the circuit is behaving, so that we will study. So whereas here in one cycle, so how the circuit will be, in the next cycle how the circuit will be. So that means this is basically the frequency of the circuit, or frequency, what frequency the circuit is operating, and if the frequency is this much, what is the response of the circuit. So that's what we discussed so far. Okay, right. So here this transient analysis, so that comes under the time domain analysis, right? So if you have time domain analysis, so that means, so these, to solve these things, so we normally use the differential equations. For solving this time domain circuits, we use differential equations. So differential equations to solve this time domain analysis, right? So what exactly this transient is, so let us see. So one simple circuit. So we have some capacitor here, right? On the other side, so we have some circuit like this. So we have some switch here, some switch S. So let us assume that this is 20 volts. it has comes a capacitor, 1 farad is there. So this resistor, some 2 ohm resistor is there. Okay, right. So now tell me one thing, right? So if we energize a capacitor from the DC source, if we energize a capacitor for a DC source, so is it open circuited or short circuited? We discussed this, right? When we are discussing the omega L and omega C concept, XL and XC concept, we discussed some things. So those are related to frequency, right? So when the frequency is 0, right? When the frequency is 0, so how the capacitor will act as? What is the value of XC? So when the frequency is 0?
Infinite.
So infinite, right? So that means it acts as infinite resistance to the DC supply. So whereas XL,
0.
0, right? So what is the meaning? So this capacitor will act as a open circuit for the DC supply. So whereas this inductor will act as a short circuit for DC supply. So this is what we concluded on that day, right? So this capacitor acts as a open circuit for the DC supply, and the inductor acts as a short circuit for the DC supply. A simple example, right? So let us assume that, so we have some circuit like this. Okay. Okay, we'll come back to that later. So this is the thing. So just remember, right? Okay. So this is under what condition? So this is under steady state condition. So this is under steady state. So there is no change in the circuit. Okay, the circuit is remain same all the time. So whereas here, so what transient means? So here at this particular time, so this is the circuit. And for example, sometime, right? So let us assume that. So we have switch here at t equal to 0 seconds. For example, t equal to 0 seconds. This switch is closed. This particular switch is closed. Understood? At a particular time t equal to 0, the switch is closed. Right. So now what we have to study is, so how this capacitor is behaving, how this capacitor is behaving. Capacitors basically store the energy, right? So capacitors, so basically store the energy. For example, you have circuit something like this. If you connect a capacitor here, right? So this is a 20 volts, right? So now tell me, what is the voltage across, or what happened to this capacitor? If for example, here some 2 ohm resistor is there. So what happened to this capacitor? Or what is the voltage across this capacitor?
20
What is the
voltage.
voltage across this capacitor? So
20
this is
voltage
20 volts, right?
steady
So
state.
why? So this capacitor acts as a open circuit, right? So what is the equivalent circuit of this one? So this is the one. This capacitor is open circuited here, right? So what is the voltage here? This is 20 volts. What is the voltage in the circuit? What is the voltage here?
20 volts.
Just use the open circuit voltage 20, right? So here, so there is no drop in the current because there is no voltage drop here. Why no voltage drop? So there is no current that is flowing through that. So that's why whatever the source voltage is there, so that same voltage is here. So now anyone tell me what is the voltage across this capacitor? So voltage across the capacitor is 20 volts, right? Understood?
Yes.
So that means the capacitor is charged to 20 volts. The
Yes, sir.
capacitor is charged to 20 volts, right? So now the thing is that, so how the 20 volts is reached? Okay, so how the 20 volts is reached, so that we're going to study now. So there is a property to the capacitor, right? So capacitor will not allow. So if you assume that if this is the time, right? So here this is 20 volts. So how it is reached to 20 volts, so that you are going to study. Right. So this is, there is a property to the capacitor, right? So capacitor will not allow sudden change in the current, right? So that we discussed. Understood. Similarly for inductor, will not allow sudden change in the current. Inductor will not allow sudden change in the current. Similarly, capacitor will not allow sudden change in the current. In capacitor will not allow sudden change in the voltage. Okay, so what we are studying is, for example, if you connect a switch here, right? Switch here. Okay. So this switch T equal to 0. So we have some voltage Vs here, some R here, and C here. Okay. Right. We have time scale here. So this is the point. So where T equal to 0. So this is starting from minus infinity. Somewhere you have plus infinity is there. So this is a time scale. Right. But T less than 0, what is the fate of the switch? Whether it is on or off?
Off, sir.
So here the switch off, right? So this is the point where the switch is on here. So now at T equal to 0 or T less than 0, what is the voltage across capacitor?
So VS.
Zeros.
Zero, sir.
Why Vs?
Zeros.
So 0 volts,
Zero,
right?
sir.
Because there is no physical connection. Okay. So this circuit is different, the source is different, right? At T equal to 0, right? At T equal to 0, what is the voltage across the capacitor?
20 volts.
20 volts. But one thing we studied that so capacitor will not allow sudden change in the current, sudden change in the voltage, right? So that means, so if you draw a graph, if this is the voltage across capacitor, let's assume that this is Vc. Okay, so you have minus infinite here, 0 here, so you have plus infinite is there, right? So what the graph will be? So how the graph it will be? Will be. So that means this will be 0, right? Okay.
Yes,
Understood? Right? So now what is the voltage at 0 voltage?
Zeros.
Zero.
At 0 also, so this is dV by dt, right? So capacitor will not allow sudden change in the voltage. So instead of that, if you have a resistor circuit, so automatically, so this is whatever this value, the current will automatically will rise, right? So inductor will not allow sudden, so capacitor will not allow sudden change in the voltage. So whatever the voltage here, so same voltage here, right? So now the question is, so when it will reach to, right? When it will reach to 20 volts, when it will reach to 20 volts, and how it will reach to the 20 volts, or how it reach, when it will reach to this Vs, or how it will reach to this Vs. So that is, or that we are going to study now, right? So here, so this is the transient analysis, some infinite time. So that means it is reached to this 20, this Vs, whatever this Vs is there, right? So this Vs value. At some point of time, it is practically reached to this end voltage. So that is Vs. So how it is reached, so whether it is reaching like linearly or whether it is reaching exponentially or how it is reaching, so whether it is reaching like this, okay, or whether it is reaching like this, so that we are going to study now. Okay. So when the closed switch is closed, right, so how the capacitors are charging, right, so how the inductors are, how the current across the inductors are varying, so that we're going to study now. So how it is varying, so that we'll discuss in this subject.
Sir,
Yes.
sir, recording has been resumed, sir.
Yeah, I resumed. Right. So here, so how exact it is reaching to the final value. So this is the final value, right? In other words, it is known as the steady state value. So this initial value is 0. From that, this capacitor is reaches its final value, so which is equal to Vs, right? So same case here also, this capacitor initial value is 0, from 0 to 20 volts. So how it is reaching? So that we will study in this subject, right? So here all these things are studying by using the differential equations, right? By using differential equations we'll study. So therefore, based on the order of the differential equation, so we have first order circuits. So these first order circuits, so these are characterized by first order differential equations. So these are characterized by first order differential equations. What is the first order differential equations? Something like this, dv by dt plus x, something like equal to y, something like this, right? This is the first order differential equation, right? So here the order is only, we have only one derivation, one derivative term is there. Similarly, we have second order circuits. So these are characterized by second order differential equations. So these are characterized by second order differential equations. Something like that. We have d square v by dt plus dv by dt plus v into something like this. So here the order is, we have 2 times the derivative. So this is the second order of differential equations. Okay. So here basically the first order differential equations, if you have only one energy storage element, either capacitor or inductor, if you have only, if L1 inductor is there or one capacitor is there. So if you have only one energy storage element, so that means that is categorized as, that is characterized as a first order differential equation. If you have two, right, if you have two energy storage devices, L and C, so both are there in the circuit, so it is basically comes under the second order circuits. Okay. In first order circuits, you have only one energy storage element, either you have a capacitor is there or an inductor will be there. In case of second order circuits, you have two types of energy storage devices, that means inductor and capacitor, both will present. Okay. So there is a one certain cases, right? There are certain cases, even though you have two energy storage elements, but the circuit will still be in the first order only, right? So there are some special cases. So even though the circuit is having two types of energy storage elements, so that means inductor is there, capacitor is there, but still the differential equation of the circuit is in the first order only, right? Okay. So not necessary be second order. There are some exceptions are there. Understood? Understood.
Yes, sir.
Okay. So first we'll start with some basics of, right, we have different circuits are there. First we'll start with series RC circuit. Series RC circuit. So we'll start with first order transients. So first order circuits. So we'll start with series RC circuit. We'll start with series RC circuit. Yes.
Sir, here we are using DC transients, no, sir?
Yeah, we'll start with DC transients. That is first order. So we'll start with DC transients. So in this, we'll start with first order. So right now we are discussing with RC circuit. Okay.
Okay.
RC circuit. Again, we have two types. So one is the natural response and another one is forced response. Okay. So meaning of natural response is the circuit is not energized. The circuit is not energized from external source. Right. So whereas forced response, the circuit is energizing from a external circuit, which right now we are here. Okay. So before that, so we'll discuss some of the basics of these circuits. So come back to the circuit again. Right. So come back to the circuit again. right? So only one thing you remember, keep in mind that so capacitor will not allow sudden change in the voltage, right? So how exactly? So we will put that in mathematics form. So that means in the same circuit here, the switch is closed at t equal to 0, right? So that means just before the switch is closed, what is the voltage across the capacitor? So that means V of 0 minus. What is it meaning is, what is the meaning of this one? The voltage, this VC. So voltage across capacitor just before the switch is closed. What is the voltage? What is the voltage?
0 volt.
0 volts, right?
0.
Similarly, at the instant the switch is closed, what is the voltage?
0 only.
0
Zero,
only,
sir.
right?
Yes, sir.
And another one, so just after the switch is closed,
Zero.
So 0.
Zero, sir.
0.
again it is 0 only, right? Okay. So this is the meaning of the capacitor will not allow sudden change in the voltage, right? Just before the switch is closed, at the instant the switch is closed, just after the switch is closed, the voltage is 0 only. Okay. Similar case, let us assume that in the same circuit, so this capacitor is already pre-charged, right? So which is the voltage V0. So this is the initial voltage across the capacitor is V0, right? So the initial voltage across the capacitor is V0. So now tell me what is VC of 0 minus VC of 0 and VC of 0 plus.
All V not.
All are equal to V0. So that means this curve will be something like this. Okay. So this is, you have V0 here. Okay, we have V0 here. So from this V0, it will reach to its final value. Its final value is Vs, right? Its final value is Vs. Okay. So that means whatever the energy or whatever the voltage that's stored in the capacitor, so that is retaining at 0 minus instant, 0 instant, or 0 plus instant. So this can be what is stored energy. This is also 0 of C V0 square, right? Agree?
Yes, sir.
Okay. So this is also equal to W0 minus, this is also equal to W0 plus. Right? So these things is only valid for capacitor. So whereas for resistor, this is entire thing is wrong. For capacitor or inductor is also, so this entire thing is wrong. For per inductor, so inductor will not allow sudden change in the current. Right. So that we will discuss in later classes. Let us assume that you have some circuit like this. So this is C, this is R, right? So we have some switch here. So this switch S. So this switch is closed at t equal to 0 instant. So right now we are talking about series RC circuits. Understood? Right. So assume that, so there is no source. Assume that there is no source, and also the capacitor is charged to a voltage, or capacitor is initially charged to some voltage V0. So the initial voltage across the capacitor is V0. So how exact it is charging? We have some other circuit is there. From other circuit, this capacitor is charged to V0. Right. The voltage or the initial voltage across the capacitor is V0. Right. So it will be something like this. So we have t equal to 0 here. T equal to 0 here. Right. So this value is, what is the value of this? This is VC of t. Right. This is VC of t. What is the value here?
V naught.
V naught,
V
right?
naught.
So this is time is progressing, and this is from minus infinite. So we have this graph is started. Somewhere you have a plus infinite is there. Somewhere. All right. Understood? At t equal to 0, the switch is closed. T greater than or equal to 0, or for t greater than or equal to 0, so how the circuit will be there? So this will be the circuit, right? The switch is closed now. So this is the circuit, right? Agree?
Yes, sir.
This is the circuit, right? Everyone agree?
Yes, sir.
Right. So now, right. So this is the circuit somewhere. See here, some node is formatted here. So let us assume that. So this is the capacitor current IC. So this is the current IR. Okay. So this is IC and IR. So why I am denoted with smaller, usually this is DC circuit, right? So we supposed to denote it with a capital letters, right? So instead of that, I'm using a lowercase letters means, so these are time varying, right? So these are time varying. So that's why we are denoted with a lowercase letters, right? If you apply KCL at this point, so what you got? So IC plus IR equal to 0, right? Agree?
Yes, sir.
Okay. So what is IC? If you know the voltage, what is IC?
E by XC, sir.
If this value is C, what is IC? You know the voltage across capacitor. So what is capacitor current? Yes,
D by
yes.
dt of charge across capacitor.
Will it be like this? C
Sir,
into
IC is equal to, sir,
dV by
I naught
dt?
into E power minus T by 2. Yes, sir.
Will it be like this? C into dV by dt?
Yes, sir.
Yes, sir. Yes, sir.
Okay. What is the voltage or what is the current through the resistor? If you know the voltage,
IR into R.
VC by R, sir.
V by R, right?
VC by R. Yeah, V by R.
V by R or VC. Okay. Just for simplicity, I have written like this to an unnecessary. So this VC of T, so I am writing as V. Okay. Don't be confused that. Understood? Instead of writing VC of T, I'm just writing V of T. So that will give unnecessary confusion. So this entire thing is equal to 0, right? Understood? Right. So what kind of differential equation it is? What is the order of this differential equation?
So
First
first
order.
order.
So first order, right? So that means if you have one energy storage element like capacitor, so this differential it is forming a first order differential equations, right? You're
Yes,
aware
sir.
of these
Sir.
things, right? Okay.
Yes, sir.
Okay. So then my work will be simplified. So now, right, our objective is, what is our objective is, we need to find out the voltage across capacitor, right? At every instant, what is the voltage across capacitor? So this is how, if the time varies, so how the capacitor voltage will vary. So that we are going to find out, right? So that means what, how to find that? So we need to integrate this one, right? So next step is integration, right? So we have one side, so dV by dt V, and the other side, so minus of dt by RC. So now tell me what are the limits here? What are the limits of this
T
circuit?
equal to
So V
0.
naught to
V
V
equal
and
to
so
V naught.
0 to T.
Right. So here, time, this is time one side and the voltage on the other side, right? If the time varying from 0 to, right, some time, some finite time t, right? If the time is varying from 0 to t, what are the limits for the voltage? If 0 voltage, what is the voltage across the capacitor?
V naught.
V naught, right? At t time, what is the voltage across capacitor?
From V.
Vc of t. Understood?
Yes, sir.
So this is important step, right? So here our ultimate aim is to calculate the voltage across the capacitor when the time varies, right? So here we need to fix the limits when the time varies from 0 to t. So how the capacitor varies from its initial value V0 to some value Vc of t. Understood? Right. So now what is the value here? If you differentiate this one, what is 1 by V into dV? What is the value here?
Log V.
Sir, ln. Sir,
ln
ln
V,
V
right?
by V no.
Its initial value is V0 and this is Vc of t. What is the other side?
Minus T by RC.
Minus t by RC. So what is its limits? So this is also vary from 0 to t. Clear? So what is the first term? What is the first term?
Substitute
ln
upper limit.
Vc of
ln
t, right? Minus ln
ln
V0,
V0.
which is equal to minus t by RC, right? Agree?
Yes.
So this can be written as ln into so Vc of t by V0. Is it correct? Minus
Yes.
t by RC. So from this Vc of t by V0, so what is its value?
E to the power.
E power minus. E power minus
E
t.
to the power of minus t by RC, right? So from this Vc of t, so which is equal to V0 into e to the power of minus t by RC. So this is the one, right? So this is the one. So how exactly the capacitor is changing? So how exactly I'm just erasing some portions here. Oh, no. Wait. I will write it in the next slide. Okay. So how exactly the capacitor voltage is varying? So Vc of t equal to V0 into e to the power of minus t by RC, right? Understood. So now tell me, so how this curve look like? So this is infinite time. So this is t. Right? So what is the initial value of this curve?
V no.
T equal to 0.
V naught.
V not.
So this is V0, right? What is the final value of this curve?
Sir,
We
zero.
calculate its final value when you substitute t equal to infinite.
0, sir.
Zero, sir.
So what is Vc of infinite?
Zero.
So it is 0, right? E to the power of minus infinite. So that is 0. So that means this value is 0. So how it will vary?
Exponential decay.
Exponential decrease.
Exponentially increasing or decreasing?
Decreasing.
Decreasing.
So decreasing, right?
Decreasing.
So that means, so it will be something like this, right? It will start like this. Somewhere it will practically touch us to 0. Understood? So this is the curve V0 equal to e to the power of minus t by RC. If you have some circuit like this, right? If you have some circuit like this, so this capacitor is charged to some voltage V, and we have some resistor R here. Okay, right? So initial capacitor is charged like this. What is the voltage or what is the energy stored that in the capacitor of CV naught square, right? So this is the
Yes,
initial energy stored in the capacitor, right? So where this energy, what is the final energy that's stored in the capacitor?
0.
Zero.
This voltage is 0, right? So this is equal to 0. So now where this energy is lost.
heat loss per resistor.
So that means whatever this energy is there, right? So that is transferred to this resistance. And this is dissipating as some useful or some heat in the resistor circuit. Right. Okay. So this is wasted or some it is converted into some useful work in the resistor circuit. Whatever the energy stored in the capacitor, so that is transferred to resistor, right? So where it is getting converted to useful work or it is generally just wasted, right? So here there is no excitation, right? So there is no external source to excite the circuit. So this is known as natural response RC series circuit or RC series circuit. So this is known as natural response of RC series circuit. So that means capacitor is having some internal energy, some stored energy in the capacitor. So that how that stored energy is spent, so that we calculated. Right. So how that stored energy is spent, so that we calculated. Understood? So no questions, no doubts, right? So this is known as natural response. For example,
what-
external response. Yes, yes.
Sir, what all we did just now is called natural response.
Yeah, natural response. The capacitor is having some stored energy. So how that stored energy is spent, so that we derived. Okay. If this capacitor is also energized, say this capacitor is also energized from external DC source, right? So that will be the forced response that we'll study in later classes. Okay, right. So in this, right. So here, the thing is that at infinite time, right? At infinite time, it reaches to its steady state value, right? So whenever it reaches to, so this is the steady state value. This is known as steady state value. It reaches to 0 voltage. All right. So now practically you cannot get a infinite time, right? So practically you cannot get some infinite time. So here where we define some factor known as time constant. So every time, so we cannot say that the circuit is reaches its steady state value to infinite time, right? Okay. So that's why it defines some tolerable time or some time constant that is known as time constant. So time constant of the circuit is defined as it is the time required for the response to decay to a factor of 1 by E of its initial value. One by E of its initial value. So time constant is defined as the time required for the response to decay to a factor of 1 by E of its initial value. Right. So what is the approximate value of E? What is the approximate value of E?
2.7.
2.7.
2.7.
7.
2.7 or something like that. What is the value of E? Approximate value of E? 1 by E.
0.37.
0.367, something like this, right? So what is its meaning? Right. For example, see we have V naught equal to 100 volts, right? V naught equal to 100 volts, that's the initial point, right? So here 1 by E times V naught, 1 by E times V naught. So what is its value? So it will be roughly
37%.
36.7 or 36.7 volts, right? So from 100 volts to, right, how much time required from the for the response to decay from 100 volts to 1 by E of its initial voltage, that is 37.7 volts. So that is known as time constant. That is known as the time constant of circuit, right? So here somewhere we have, what is it? What is the value here? So will it be V naught by E, right? Agree?
Yes, sir.
Yes, sir.
So now we will define the time constant. So this is corresponding value here, right? So this is time constant. So this time constant usually denoted with tau. So this is denoted with time constant is denoted with tau, right? So tau is known as time constant. Understood? Right. Okay. So now, what is the value of voltage across capacitor at this tau? What is the voltage across this capacitor at tau?
V naught by E.
Anyone?
V naught by E.
V naught by E.
V naught by E. So from this expression, right? So from this expression, what is the voltage of this? What is the voltage? So it will be V naught e to the power of per tau by RC, right? Agree?
Yes,
Agree?
sir.
No, sir.
Why no?
Minus T by tau.
Hmm.
Oh, yes, sir. सही है.
All right. So now if we equate these two, so it will be, so V naught e to the power of minus 1, right? So this is equal to V naught e to the power of minus tau by RC. Okay. Right. If we equate this term and this term, right? So that means 1 equal to tau by RC, right? Agree?
Yes, sir.
Okay. So what is the value of tau?
RC.
RC, right? So this is known as time constant of RC circuit. So this is known as time constant of RC circuit. Right. This is known as time constant of RC circuit. So where initial voltage or whatever that initial value of that capacitor is there, right? So that is reduced to 1 by E times of its initial voltage. Understood? Okay. So now, okay, so let us assume that what we derived, okay, so let us assume that we have this V naught of T by V naught. So this is right. This is some value is there. So now we'll see the significance of this time constant. We have some expression V naught of T by V naught at T equal to 0. So what is this value? At T equal to 0, what is this value?
Not. 1.
V naught of T by V naught at T equal to 0, what is its value?
1.
Sir, 1.
0.
Is 1,
One,
right?
sir.
So assume that this is 1. Okay? This is 1 only, right? V naught of T at T equal to 0, so that is 1 only, right? Okay. So now, in same way, at T equal to tau, so what is this value? At T equal to tau, so
0.367.
what is the value of Vc of T by V naught? What is its value?
1 by E.
0.367. 1 by
0.367.
E.
1 by E, right? So that means it is roughly 0.36788 into, that will roughly like this. Okay. So this is at T equal to tau. Similarly, at T equal to 2 tau, so what is the value? What is its value?
1
At
by
T
E
equal to 2 tau.
1 by E square.
1 by E square.
1 by E square, right? So what is this value?
0.135.
0.13534. Okay. Similarly, at T equal to 3 tau, what is its value?
1 by E cube.
1 by E cube. So that is roughly 0.04979. Okay. Similarly, at T equal to 4 tau, so what is its value? So it will be roughly 0.01832. Similarly, at T equal to 5 tau, so its value is 0.00674. Okay? 0.674. Meaning is, right, at T equal to 0, if this is equal to 100%, right? So this is how much this is? This is the 37.7% only, right? So what is this one? So this 13.5% only. So what is this one?
4%.
Roughly it is 5%, right?
5%.
4.9, so roughly 5%. So what is this one?
So roughly 2%.
So roughly 2%, right? And what is this one?
Roughly 0.6%.
So it is almost zero, right?
0.
Almost zero, right? Okay. So what we studied is at infinite time, right? It reaches to zero, right? Or it reaches to its final steady state value. So now tell me practically how much time constants are required to reach zero value? How much time constant you reach? For example, you started with 100 volts, right? So what is after 5 time constants? So what is its value? Almost 0.6 volts, right? Agree?
Yes, sir.
See, when compared to this 100 volts, this 0.6 volts is insignificant. There is no much value for that, right? So that means theoretically you required infinite time to reach the steady state, but practically you require 4 to 5 time constants. Practically you required 4 to 5 time constant to reach the steady state. Understood? Practically you required 4 to 5 time constant to reach the steady state. So this is one of the important thing. So how, understood? So this equation can be written as in terms of V naught e to the power of minus t. What is RC? RC is known as
Constant.
tau, right? So this is tau. Okay, Vc of t, V naught into e to the power of minus t by tau. So what is the expression? Vc of t equal to V naught e to the power of minus t by tau. So where this tau is time constant, so this is equal to RC. Right. And another thing you need to remember that you require 4 to 5 time constant to reach the steady state value. Practically. But theoretically you require infinite time. But practical thing you require just 4 to 5 time constants. Alright. So that is one significance of this time constant. So there is another significance of the time constant. Right. So we have some time constants are there. So one is 0.5. Another one tau equal to 1. So here what are the units for this time constant? What are the unit for time constant?
Second or
Seconds, right? Seconds. So let us assume we have tau equal to 2 seconds. Right. So we have some graph is there. Right. So here voltage across capacitor, so that will be V naught into e to the power of minus t by tau. So that is the formula, right? Okay. So now we'll draw for these three cases, right? So obviously the initial point is same for all, right? Agree? So this with respect to t. Obviously the initial point is same for all, right? Understood? So now we have three. So these three, obviously we have three paths will be there, right? So we have three paths. So here the first one, it may be the first one of the thing. It may be another one. Right. So now tell me, so which is corresponding to 0.5 seconds, 1 second or 2 seconds?
The red one is for 0.5 and purple one
The
for
red
2.
one is for 2 seconds.
Why?
Red one is 0.5 because it is taking less time to reach the steady state, and 5 into 0.5 is least among all the three.
Yeah, right. Simple logic, right? We have time constant, right? The time constant. So which one, which is having low time constant, right? So what is the meaning? It requires less time to reach the steady state value. Understood? It requires less time to reach the steady state value. In other words, all of these things. So here, this one, for example, if it started at 1, so it require the first one require only 0.5 seconds to reach its 1 by e value. So whereas here it requires 1 second to reach 1 by e value, it requires 2 seconds to reach its value. That's a simple sense. So this is tau equal to 0.5 seconds. So this is corresponding to 1 second. So this is corresponding to 2 seconds. Understood? Understood.
Yes, sir.
Okay. So there is another
Yes, sir.
analogy, right? So let us assume that. So we have circuit like this, right? So this capacitor C value is fixed here. Let us assume that C value is 1 farad. So we have two cases for R, right? We have RC is the time constant, right? So one case is 0.5 ohm, second case is 1 ohm, and third case is 2 ohm. Simple logic, right? So what is the first one time constant with this one? What is the tau here?
0.5.
5 seconds.
0.5 seconds. For this case, it is 1 second,
Second.
right? And for this case, it is 2 seconds, right? So here, this resistance value, the capacitor value is fixed here, and the resistance values, I had three possibilities, either 0.5 second, 1 second, or 2 second, right? So now thing is that, so this resistance, okay, if this is the resistance, so this is having the lowest, or this is having the largest time constant, right? Because the resistance value is more, okay, so the current will be less. The current will be less, so that's why it is taking more time. Understood? Okay. So this is how the time constant, if the smaller the time constant, more rapidly the voltage will reduce to, right? If the smaller the time constant, the voltage will reduce to more, or voltage will reduce at a faster rate. The voltage will reduce at a faster rate. So now the thing is that we will calculate IR of T. What is IR of T in this circuit? What is IR of T? So this is
VR.
IR, right? What is the value of this IR T of T? So it will be VC of T by R, right? Agree?
Yes, sir.
Okay. So what is this value? VC of T is V naught by R into e to the power of minus T by tau, right? Agree?
Sir, but this is when those are in parallel, no, sir.
Why parallel?
Because then only it will be the voltages will be same.
So this is VC of t, right? Okay. So
Yes, sir.
obviously this is also VC of t, no?
Yes, that is
So
possible
here
only
there
when
circuit will be parallel only, right? Okay. If you do, we can. That means it forming a closed circuit. You cannot say whether it is series or parallel.
okay,
Understood?
sir.
It's a closed circuit, right? If you see, so this side look like parallel, but actually these two are in series, right? So that means it's a
Yes,
closed
sir.
circuit.
Okay, sir. Understood.
Understood. So this is agree? You agree for this?
Yes, sir.
So now,
Yes, sir.
so how exactly it look like? So this is the current through the resistor. So how exactly it look like? What is the initial
Same
value?
exponential decrease.
The same, sir.
Same, right?
Yes, the same.
So that means its initial value is V naught by R. So it will be something like this. Understood?
Yes, sir.
Okay. So now I'm erasing this. So now what is the power delivered? So P of T. What is the P of T in this circuit? Power delivered to the resistor. What is power in the resistor? Or the power dissipated in resistor?
Sir, IR square, sir, into R.
So what is the power dissipated? So here voltage, you know, right? VC of T square by R, right? Agree? You agree for
Yes,
this?
sir.
Hmm?
Yes, sir.
So what is this value? Will it be V naught square by R? So we have one R get cancelled, right? It will be minus 2 T by tau. Is this correct?
Yes, sir.
Hmm? Is this correct?
Yes, sir.
Right. So now what we understand that whatever the energy stored in the capacitor, so that is absorbed by the resistor, right? Energy stored in the capacitor, so that is absorbed by the resistor. So now energy stored in the capacitor, so that is right. So it will be integration of this one, right? So it is integration of this power that gives you the energy, right? Agree? Integration of power gives you energy, right? So here some d lambda, so where this one is changes from t. Understood? Or some x. You're okay for this?
But
Sir,
Sir.
here
dt
you have
should be the
denoted PR as the
P
function of
PR of
X.
T dt.
Here is a function of x, right? So just to avoid the confusion, instead of that t, I have written x. Okay. Some x is some dummy
Okay,
variable,
sir.
right? So here, the simple thing, right? You know the power, so integration of the power, so that gives you, right? For example, this simple logic, the power is varying like this. Okay, so this area will gives you the energy, right? Understood? If this is the power curve, the area of that one, so that gives you the energy in what? Energy, right? The simple things, right? So here, so now how to write this one 0 to t. So this will be V naught square by R into e to the power of what is this value? Minus 2x by tau into just dx. You can also use t, so that may create some confusion. So that's why I omitted. So what is the value of this one? Anyone? What is the value of this?
Sir, V naught square tau upon 2R
V naught square by tau.
tau. Sir,
Yeah.
numerator in tau
Okay. Tau
upon
by
2R
2r
into 1 minus e raised to
into 1 minus e to the power of
minus
minus
2t by tau.
yeah. This is tau, right? What is the value of tau? Tau is RC, right? If you
Yes, sir.
simplify this one, what you will get here? Of tau CR, right? RC rate. One R get cancelled. So you left it of CV naught square. Agree? 1 minus e to the power of minus 2t by tau. Is clear? So this is how the power is dissipated or how the power is absorbed by the resistor up to time t. Up to time t. Right. So when t equal to 0, right. So when t equal to 0, so what is the power that is absorbed here?
Of CV naught
0.
square.
If t equal to 0, what is its value?
0.
Yes. At t equal to 0, so what is the value of this one?
0.
What is the
0.
value of this one?
0.
1.
So this
Zero.
entire thing is e to the power of 0, right? What is the value of e to the power of 0? So that is 1,
One.
right?
1.
So that means 0. So this entire thing is 0. Meaning is at t equal to 0, so there is no power absorbed in the resistor. Right? Whatever the energy stored in the capacitor, so that is of CV naught square, so that is present. Similarly, at t equal to infinite, right? So what is the value?
RCV not square.
CV naught square.
Of CV naught square, right? So this is entire thing is 0. So that means what you understand from that? So what you understand from that?
Whole energy is absorbed by the resistor.
Whole energy, yeah, whole energy is consumed by the resistor. The whole energy is consumed by the resistor. Or whole energy is absorbed by the resistor. Whatever the energy there present in the capacitor, so that is absorbed by the resistor. Whatever the energy present in the capacitor, that is absorbed by the resistor. So now the capacitor is, there is no energy left in the capacitor. That means the capacitor energy is 0, right? And the energy absorbed by the, don't say that energy stored by the resistor. So energy absorbed by the resistor is of CV naught square at infinite time, right? So someone may ask the questions, so regarding that at t equal to 3 seconds or t equal to 0.3 seconds, so what is the energy that transfer to the resistor? So they may ask questions like this, right? So that's why we're deriving this expression. Okay. So meaning is at omega, or this is the energy stored at infinite time. So this is equal to of CV naught square. So this is equal to energy stored in the capacitor at initial time. Okay. So now omega C infinite. So this is equal to 0. Understood? So this is how the power or how the energy flow is taking place between the capacitor and the resistor. So you have any questions? You have any questions?
No, sir.
Okay. So we'll stop here.